All right, good afternoon everyone. I'm Saurabh and I'll be talking about hardware acceleration in ZK. Some of you might already be familiar with this. This is going to be a quick lightning talk, right? And it's a fun topic and hopefully you get something out of it, right? So this is the quick agenda of what this talk is going to be about. I'll be talking about what exactly is meant by hardware acceleration and how it fits into the ZK landscape, right? We'll be quickly going over some of the primitives that these accelerators try to solve and what actually are the hardware resources that are required to build these accelerators. What is the current state of hardware acceleration in 2023 for ZK, and what is the research looking like? What are the future directions that we will go from here, right? So yeah, by the way, who here has worked on hardware acceleration, something like GPU?
We lost Harold.
Oh yeah, okay, all right, cool. So so hardware acceleration is trying to use some sort of dedicated hardware, right, to accelerate some parts of your computation, and that could involve tailoring your algorithms to fit a particular hardware. So maybe writing so let's say you're planning to deploy something on the GPU, right? So you probably have to use some sort of framework like CUDA that NVIDIA provides, right, to kind of tailor your algorithm to do that. And it may also involve creating new hardware altogether in the form of ASICs, right, custom hardware to do certain specific tasks, right? And this is not a new thing. This has been going on for many decades now. In ancient times, right, we used to have these coprocessors for doing floating point operations on a lot of mainframe systems, right? So along with normal computation, you want to speed up some floating point arithmetics, right? So we had hardware accelerators starting with something like FPUs, and today almost every computer has these DSPs which accelerate your audio and video. All the devices have GPU for gaming, video encoding, decoding, right? And then there are these other set of accelerators as well, like TPUs, that Google provides for accelerating ML, and we have these networking chips as well. And the last one is what we are interested in, right? The cryptography acceleration. So traditionally, this is what hardware acceleration for crypto has looked like. Traditionally, I think two areas have been of most focus: the hashing and the encryption, right? So every chip these days has dedicated hardware for running these AES encryptions and doing SHA-based hashes, right? But I think the most famous hardware accelerator that everybody has heard of is the Bitcoin mining rigs, right? So billions of dollars have been spent on creating these Bitcoin ASICs, right? But then there are these novel crypto primitives that have emerged and which will really benefit from hardware accelerators. So something like FHE, verifiable delay functions, and zero knowledge proofs. And we'll be focusing on the zero knowledge proofs part for today, right? So so why do we actually care about hardware acceleration for ZK? So this was a quote that was published by Justin Thaler. He said that proving something takes over 1,000,000 times more computation than just running that computation in the first place for a lot of ZK proofs. So running a SHA hash on your machine might take few milliseconds, but creating a proof, right, might take up to 1,000,000 times more time than that. So clearly we need to do better, right? And hardware acceleration helps us with that. And these are again some practical numbers of what ZK proofs look like and how hardware acceleration helps. So something like ZK AVM, right? So Polygon takes about 40 minutes to compute a zero knowledge proof, and it takes about 1 million of gas to generate that. But in comparison, Polygon runs over 10 million gas per second, right, natively. So this is what it's computing, and this is the time it takes to generate the proof. So there is like a 25,000 overhead for running the computation and verifying that. Similarly, for RISC-0, today we have state-of-the-art chips that run at 5 gigahertz, but the proofs are only running at somewhere around 50 kilohertz, 500 kilohertz. So again, we have like 10,000, 100,000x overhead, right? So, again, this is why we need hardware acceleration, right? And these are some of the goals that that we have when we create these hardware accelerators. We want to maximize the amount of throughput. What that means is we want to maximize the number of operations that can occur in a particular batch of time, right? We want to reduce the cost of it. That may be just the OPEX or the CAPEX cost. So if you're building like a Bitcoin mining rig, right, you want the capital expenses to be low, and it has to be really power efficient so that you can save money. And you also want the latency to be low, right? So something like a ZK bridge, you want quick finality of the transaction. So you don't want to wait too long for the ZK proofs to generate. So these are some of the metrics that we are interested in when we design hardware accelerators, right? And what actually needs to be accelerated in the first place for specifically for ZK, right? So every ZK proof system today has some sort of flavors in these three aspects. So it may not include all three, but majorly these are the three main bottlenecks when it comes to proof generation: the multiscalar multiplication, the entity, which is basically FFTs for which run over finite fields. It's called number theoretic transform, and the hashing. Right. I think everybody kind of knows what MSMs are, so I wouldn't go over that. So it is basically trying to multiply elements together and adding all of them at the end. But the good thing about MSMs is that they are highly parallelizable. You can split those things across multiple chunks and accumulate all of them together at the end. So it is very amenable to something like hardware acceleration, wherein you can parallelize the whole thing across many GPUs or hardware accelerators and eventually accumulate all the intermediate results together at the end. Right? And if you're doing something like MSM, you can do a whole bunch of other optimizations, like using the Pippinger's algorithm, which reduces the complexity from linear to O of n divided by log n. You can also play around with different form of curve point representation, which can maybe reduce the number of field operations. So instead of doing, you can, there are these other representations such as affine Jacobian, right? So which can sometimes give you some sort of optimizations and speed ups for the MSMs, right? But at some point, it's not about the compute that is the limiting factor for MSMs. At some point, it becomes the bandwidth actually. So the way CPU and GPUs work is that you have to kind of transfer the data from your memory to the GPU's memory, and transferring that is sometimes very bandwidth intensive, and eventually in MSMs, right, at some point instead of the computation, the communication and the network latency becomes the major bottleneck. Right. So coming to the next primitive, which is the entity, which, as I mentioned, is just a fancy word for FFTs that operate over finite fields, and using fast Fourier algorithms, and these are primarily used for multiplying polynomials together, right? This is why we need entities in ZK, and unlike MSMs, this one is not efficiently parallelizable. You need a lot of memory because this one involves a lot of random access to the memory, and again is bandwidth intensive. And the last one is the hashing primitive. So a lot of the times we want to prove that we know pre-image to a hash in our ZK circuit, and we don't usually use the normal SHA-256, SHA-3 hashes, right? In ZK, we usually use something like Poseidon or Rescue Prime hashes because they have lower number of constraints compared to the SHA hashes. And again, we can these hashes can be constructed by changing a lot of parameters internally. So we can tweak the field size, the number of rounds, the 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 size of the field, right? So based on that, we can create different versions of hashes, and all of them have different trade-offs. So, oh yeah, so just bringing all of these together, right? These three primitives are what actually matter in for hardware acceleration. And if you just look at some quick stats, right? If you look at snarks, most of the time is spent on the MSMs and the entity operations. Whereas if you compare that with Starks, we don't have a lot of MSMs there, but most of the time is taken by the entity and the hashing operations, right? So in general, if you see Starks or the Fry-based Starks, right, the major bottleneck is FFTs, but if you go down and if you compare that with something like Plonk or Marlin, most of the time is spent on MSMs, right? And all of these operations, right? So when we consider ZK snarks, eventually they have these primitives like MSMs and entities. And if you come down one more layer down the stack, you will find that most of the operations at the ground level are just these modular multiplications. So eventually when we go down to the most bottom level of the stack, what we are basically trying to optimize is the amount of modular multiplication operations that we can do, right? So this is the real metric that we are concerned about. And right, so eventually it comes down, the workload eventually comes down to the modular multiplication, and we can estimate the performance of a hardware based on how well it does these modular multiplications, right? So what is the, right? So I think if you take something from this presentation, I think this probably is like the most important slide, right? So I'll quickly walk you through what this actually means, right? So like I said, modular multiplication is the most important operation that happens in ZK, right? So how we gauge a hardware acceleration will perform is based on all of these metrics. So we can just quickly take a look at how many cores does these things have. What is the size of the registers? Like how much can we actually multiply in one single instruction, right? And what is the frequency of the chip? So based on that, we can calculate like what is going to be the power of the modular multiplication operation. So take desktop computers for example, they have 8 cores, and we usually can do 64-bit cross 64-bit operations at 5 gigahertz speed. So and there are these things are quite inexpensive these days. So it gives you a score of 0.01. So this one calculates how powerful is it and how much money you're spending, right, based on the power consumption. Compare that with something like a server machine. So although you have a lot of cores here, these things are quite expensive actually. So you can see that the overall cost of this is lower than desktop computers. But then if you look at FPGAs, right, FPGAs and GPUs, these things have massive number of cores internally. These things have massive number of cores, but the multiplier size is probably smaller than the desktop computers, and these things cost a lot more than the desktop computers, but this is the number that we are concerned about. So higher the number, the better it is. So you can kind of see that GPUs as of today 2023 give you the best performance per dollar, and that may change in the future once we have better ASICs and FPGAs, but yeah, today I think GPUs dominate based on these results. And if you're interested about these kind of data, right, I probably recommend this video which went more into these statistics. Right, but at some point we hit acceleration limits. At some point it's not just the computation of these multiplication that is the main bottleneck. At some point it's also the memory, right? So sometimes we are not able to fit everything in our working memory, right? So and sometimes the communication between your chip and the hardware accelerator again becomes the major bottleneck, right? Yeah. Okay, yeah. I think I'm nearing the end of the presentation. I'll maybe just quickly end with an example for Filecoin, how it's using hardware acceleration in practice today. So I think Filecoin is an example of something that is working in real world today and generating the highest amount of zero knowledge proof volume, I think. And it uses something called as proof of replication, which says that your data has been properly stored in the blockchain network, right? And for doing something like this, the Filecoin uses a lot of Poseidon hashing, creating zero knowledge proof over a lot of hashes, and doing that locally will take you 100 minutes, but using something like GPU, right, they are able to achieve this in 1 minute. So you're getting like a 100x clear speed up here. And they also have 10 Groth proofs, each of 130 million constraints running, and doing something like that on your CPU with lots and lots of cores will take you 60 minutes, but the folks at Filecoin are able to do it in 3 minutes using GPUs again. All right, so this is what like the current state of ZK hardware acceleration looks like, right? But clearly we can do much better from here. This is not, we are not at the end of history. There is so much more. There is so much more room for improvement in hardware acceleration, right? So these are some of the pointers where things can go. I expect things to change a lot in the next year. There are a lot of people working on improving the current state, right? So you can probably have better algorithms and implementations for the low-level primitives, right? There is always room for improvement in the underlying proof systems itself, so you can have lower number of operations. So rather than some proof system taking maybe 10 MSM operations, you can optimize that to take lesser number of operations, right? So these are some research areas, and then you can simplify the proof to reduce the number of MSMs, reduce the number of communication between the devices and the accelerator, and I think we might have ASICs once these protocols kind of ossify in the next few years. Right now, nobody is really building on ASICs, but maybe if the proof systems get more mature over time, we will probably move towards ASIC, just the way we did with Bitcoin, right? So yeah, these are like the future directions where things can go. And with that, I think I come to the end of the presentation. Thank you.